be doing a strong acid, strong base titration problem. The purpose of a strong acid, strong base titration problem is to determine the concentration of either solution by titrating it with an acid or a base of known concentration until neutralization occurs. Neutralization is when the acid has completely reacted with the base, which is when the equivalence point has been reached. Strong acids and strong bases are soluble in solution and completely ionized. There are 6 strong acids: hydrochloric acid, hydrobromic acid, hydroionic acid, perchloric acid, nitric acid, and sulfuric acid. And there are all the strong bases, all group 1 hydroxides and heavy group 2 hydroxides: strontium, barium, and calcium. This is the net ionic equation for a strong acid. This is the net ionic equation for a strong base. Since both acids and bases are strong, they have high Ka and Kb values and thus dissociate completely. For the purpose of this experiment, we have the known concentration as the strong base, which is in the burette, and the unknown concentration as the strong acid in the Erlenmeyer flask, but these can be switched if you would like. For a strong acid, strong base titration problem, when you add them together, this is their net ionic equation. And this also leads to a graph that looks like this: pH versus volume of base. And for all strong acid, strong base titrations, the equivalence point is at 7, pH of 7. And the equivalence point is when the strong acid has completely neutralized the strong base. In order for this titration process to occur, a few steps must be followed. And on to you, Autumn and Kestrel.
Yo, Kester, what's up?
What's up? Ready to do some titrations?
Yeah, I love to drop the base.
You ready?
Ready. How about you? So today we will be titrating a strong acid with a strong base. Our strong acid will be of unknown concentration of hydrochloric acid, and our strong base will be sodium hydroxide of 0.1 molar. Before we begin, make sure to put on your rubber gloves, your goggles, and for fun, your lab coat.
The other materials you need for this lab are a graduated cylinder for measuring the solutions, an Erlenmeyer flask for performing the titration, a beaker for waste, distilled water for cleaning your burette, an indicator of bromethyl blue, and a burette stand.
To begin titrating, make sure that first you pour the deionized water down through the burette. For 1, to clean the burette, and for 2, to make sure that this part of the burette actually works. So see how this is actually closed? When I open it, it should release the water, as it does. So that means our burette is working. Perfect. Next, we will wash this burette with the strong base. Be careful because it is a strong base. We're making sure this is closed. And it's working. Perfect. Now that we know that the burette is clean and it works, we can start our procedure. First, we'll be measuring out precisely 25 milliliters of hydrochloric acid. After she has precisely measured 25 milliliters, she will be pouring it into the Erlenmeyer flask. The Erlenmeyer flask is used because it's easily stirred and swirled during the titration. One important step that you must not forget is to add 2 to 3 drops of the indicator solution, which in this case is bromethyl blue.
Indicators are what allow you to determine when the equivalence point has been reached. They change color close to the equivalence point. In this experiment, we chose bromethyl blue because it has an endpoint at 7, around 7. And since this is a strong acid, strong base titration, that's where the equivalence point will be reached. Another way to explain this is that you want to choose an indicator whose endpoint lies on the steep part of the curve.
This is where the titration will be occurring, so it's really important that you get these steps correct. Now you will replace the Erlenmeyer flask with the waste beaker. after you have done that, we need to add the strong base to the burette. Before you add the strong base, you have to make sure that the burette is closed. If this is open, all of the strong base will be added to your Erlenmeyer flask, and you don't want that. And when you add the strong base, you need to make sure that you add enough so it's between the 10 milliliter mark and the 0 milliliter mark, so that you have enough to titrate the solution. Once you have added the strong base and have correctly added between 10 to 0 milliliters, you need to record the initial volume of the strong base.
Now that your experiment is all set up and ready, you can begin your titration. Have one person swirling the Erlenmeyer flask while another adds the base little by little in about half milliliter increments.
Now keep adding this until you see the solution in the Erlenmeyer flask change color. Since we added bromomethyl blue, this solution should change from yellow to blue. Once you see it starting to change color, once you add the strong base, you should start adding littler increments of the strong base to the Erlenmeyer flask. See, as you can see, there we go, it turned blue. This means that it has reached its equivalence point. Now that you have reached the equivalence point, you need to take the final volume of the strong base. But you need to account for the meniscus line, so make sure that you're measuring precise volumes. Once you have the initial volume and the final volume of the strong base, you can subtract these two, final minus initial, to get the total amount of base that you have added to the Erlenmeyer flask.
Great titration! Now on to the calculations!
From this titration, we collected the following data. We measured 25 milliliters of HCl, which we put in the Erlenmeyer flask. And then we measured 4 milliliters of the NaOH solution in the burette initially. Then, after we titrated the NaOH solution with the strong acid solution, we measured that there was 20 milliliters of NaOH solution left in the burette. Therefore, using the final minus initial rule, we calculated 16 milliliters of NaOH was added to the strong acid. Now that we have our experimental results, we have 4 objectives that we need to meet to calculate the pH at several different points. Our first objective is to calculate the pH before the addition of the strong base. Our second objective is to calculate the pH before the equivalence point. Our third objective is to calculate the pH at the equivalence point, and our fourth objective is to calculate the pH after the equivalence point has been reached. So, on to our first objective. In order to calculate the pH before the addition of the strong base, we need to first find the molarity of the strong acid. Because we don't know the molarity, it's an unknown acid. So, in order to do this, we need to find the number of moles of the unknown acid. So since we have this equation, HCl plus NaOH leads to NaCl plus H2O, which leads us to the net ionic equation of H plus OH minus leads us to H2O, and it is stoichiometrically equivalent, we can perform the following calculations. Since we know that the strong base had a molarity of 0.1 molar, which, to remind you, is moles over liters, and we used 16 milliliters of NaOH to titrate the strong acid, which in theory is 0.016 liters of NaOH. This leads us to 0.0016 moles of NaOH. Now, using stoichiometry, we can use this equation to calculate the number of moles of HCl. Since it is stoichiometrically equivalent, we have calculated that the number of moles of HCl is 0.0016 moles. Now that we know that we have 25 milliliters of HCl in the experiment, we can divide the number of moles of HCl over the total liters of HCl used in the experiment. This is where we calculate the total molarity of the HCl, which is 0.064 molar. Now that we have the molarity of the strong acid, which is 0.064 molar HCl, we can now calculate the pH of the strong acid before any strong base has been added to the solution. Since we know the following equation, pH equals the negative log of the concentration of the hydrogen ion, we can calculate the pH. Since we also know that HCl breaks up into H plus ions and chloride ions, we can also calculate the concentration of the hydrogen ions. Therefore, since 0.064 molar HCl, we know that the concentration of the hydrogen ion is 0.064 molar. Therefore, we can plug this into our equation. pH equals the negative log of 0.064 molar. And our pH, before any strong base has been added, is 1.19. Now, this number makes sense because since there's no strong base has been added, the strong acid should be very acidic, which means that the pH should be very low on the pH scale, which it is. Since no strong base has been added to the strong acid, and we calculated that the strong acid pH before any strong base has been added was 1.19, this is where we are on the titration curve. Now on to objective number 2. For this objective, we need to calculate the pH before the equivalence point has been reached. For this instance, since we know that the equivalence point is when 16 milliliters of the NaOH has been added, for this problem we are going to use 8 milliliters for the amount that NaOH has been added to the strong acid. So, before we begin this problem, we need to calculate how many moles of NaOH was added. Since we know that 0.008 liters of NaOH was added, and the molarity of the NaOH was 0.1 molar, we come out with 0.008 moles of NaOH. Next, we need to find how many moles of HCl was there. Since we know and calculated that that the molarity of the HCl was 0.064 molar, and there was 0.025 liters of HCl in the Erlenmeyer flask, we calculated that there was 0.0016 moles of HCl. Now that we have the moles of the NaOH and the moles of the HCl, we can use an ice problem to determine the concentration of H plus after 8 milliliters of the NaOH was added. To do this, the initial number of moles of H plus was 0.0016, and the initial number of moles of OH was 0.0008 moles. Now, since we are going to end up with 0 moles of OH in the end, we need to subtract 0.0008 moles from 0.0016 moles of H plus. From there, we get 0 moles of OH minus, and we get 0.0008 moles of H plus. Now that we have the number of moles of H plus, we can use our pH equals negative log of the concentration of H plus to determine the pH before the equivalence point has been reached. Now that we know the total number of moles of hydrogen ions in solution, we need to find the total concentration of hydrogen ions in solution. And to do this, we need to divide the total number of moles over the total liters in the solution. Therefore, it's 25 milliliters plus 8 milliliters, which gives you 33 milliliters, which is 0.033 liters of solution. When you divide the moles by the liters, you get 0.024 molar hydrogen ion. Then we can use this pH equation, which is pH equals negative log of the hydrogen ion. Then we can plug in this concentration into the equation. And when you solve, you get 1.62 pH. At this point of the titration, as NaOH is added, the pH increases slowly at first and then rapidly in the vicinity of the equivalence point. At this point in the titration, the pH is still very low, which means it's very acidic because it has not yet reached the equivalence point.
Now we'll calculate the pH at the equivalence point. So in order to do this, we need to calculate the molarity of each solution. So we first calculate moles of each one by going from the known molarity, using the volume used to reach equivalence, and then calculating the moles. And then we divide it by total volume of solution to get the molarity. And as you can see, they both have the same concentration at equilibrium. This is because it's a strong acid, strong base titration. And at equilibrium, the concentration of OH and the concentration of H plus ions will be the same, and the pH will thus be 7. At the equivalence point, an equal number of moles of the NaOH and HCl have reacted, leaving only a solution of their salt, NaCl. The pH of the solution is 7 because the cation of a strong base, in this case Na+, and the anion of a strong acid, in this case Cl-, do not hydrolyze and therefore have no appreciable effect on pH. As you can see, the middle of the steepest part of the curve is when you know that the equivalence point has been reached. In this case, it took 16 milliliters of base to reach the equivalence point. Now on to objective 4. In this objective, we're going to calculate the pH after the equivalence point. In this instance, we will have added 20 milliliters of base to the strong acid. First, we have to calculate the initial number of moles of each solution. To do this, we use the 0.02 liters of base added and change it, and use the molarity that we know to change it to moles. We can also use the molarity of the strong acid to change that to moles because we know the volume that was used in the titration. Now, we need to use an ice problem to calculate the equilibrium concentration of each solution. So, we subtract, from each one, we subtract the smaller number of moles, so that we have 0 moles of H+. This leaves us with 0.0004 moles of OH-, and that is what we'll use to calculate the pH. Now that we know the number of moles of base added, we can use that to calculate the concentration of hydroxide ions in the solution. To do this, we divide it by the total volume of the solution, which is the 20 milliliters added to the 25 milliliters of acid already present. This gives us a molarity of 0.0089 molar. From that, we can calculate the pOH using the formula negative log of concentration of hydroxide ions. That gives us a pOH of 2.05. We know that pH plus pOH will always be 14 because there's an equation derived from the equilibrium constant of water. So we do 14 minus the pOH, 2.05, and get 11.95. So we know the pH is 11.9. At this point, we have passed the equivalence point, and we have excess base in the solution. This means that the solution is very basic, and thus, we have a very high pH. This table shows the final results from our calculations. As you can see, the graph increases quite steeply. That's why, once you start to get near the equivalence point, you must be very careful to add the base in very small increments. Otherwise, since this part is so steep, it's very easy to pass the equivalence point